Well, here we go again. Time for this afternoon's stream. Carrying on with what I was doing yesterday. Designing this here bus emulating thing for testing LCD screens and what have you. If you were with me yesterday, you saw that I'd got as far as doing the firmware for the chipkit board. Don't know if it works, obviously. I've not got anything to test it with. So today I'm going to look at writing some Linux software to drive it. So let's crack on. Right. We've got the firmware that I did. So let's make a Linux directory. And how do we want this to work? Well, I'm going to be using HID API for this, which is a library that I've used before, conveniently. I've got the GitHub repo here for it. It makes working with HID pretty easy in C. I mean, there's an example program. Let's zoom in on it a bit so we can read it. It's as simple as initializing the HID, opening the device, and reading and writing. That's really all there is to it. Pretty straightforward stuff. So I want to have a program which will allow me to do individual manipulations, configure the device, and stream data in both directions, probably with some kind of rudimentary scripting almost language where I can sort of tell it, have a file of instructions to say write this value to this address, write this value to this address, read the value and display it, write this value, etc. And then just sort of log as it goes to the output, so you can see what it's doing as it reads and writes. But initially, I just want to get it to communicate and talk to the device. So let's have a look at this example. And let's have a busemu.c file, shall we? Right, so I always use stdio and unistd and stdlib, probably string as well. And of course, HID API. Right, let's just initially see if we can open the device. So we need to define our main. Okay, so what do? First off, we create a HID device handle. So HID device handle, and we need an integer for res, the result. So there you go. Res equals HID init to initialize the HID system. Looks like they're not actually doing anything with res in this. We should really check res to see that it did actually initialize the HID system, but for the moment we'll just let it fall through. I don't care at the moment if this crashes or anything. So okay, well, now we open the device. Hit open. I had OXFO55 for FOSS, free open source software, and I used 8088 if I remember rightly for the device number. No serial number, if I remember, yeah. Optionally the serial number, so we're not using a serial number for this. If not handled, print stderr. Return -1, and then hit close, handle. Is there anything to close off the... Yep, hit exit. Let's see what happens with that, shall we? And I need HID API. I might need libUSB as well. HID API not there. Why not? Maybe it's in a subdirectory. HID API.h. It is HID API subdirectory. Now, do I want to? No, what I'll do actually is add an include directory. Because I'll also want, maybe... no, there's different flavors of HID API, isn't there? Yes. There's a libUSB and a... I can't remember what the other one is, a lib or something. Flavors of it, different ways of HID API actually doing the USB communication. So name lib HID API star. Yeah, we've got HID raw and libUSB. I'm not sure which one I want to use. Let's use libUSB. That compiled. Does it run? Unable to open it, of course. But that would be because it's sat here. Can't open it unless I plug it in. Right. See what happens now when I plug that into there and run the program. That opened it. That's looking good. Right. So let's create a wcharty. Max str is 255, I think it was. 255, yes. So if we get HID get manufacturer string handle wstr max str. Actually, let's change this. I want two here. I want mfg and prod. mfg and HID get product string handle prod max str. Found ls, isn't it? ls bar from %ls prod mfg G. Found bus emulator from Majenko Technologies. Working. Okay. Progress is already being made. Now, what I should do next is writing OX55 to OX00. So a 2-byte buffer. First byte, if you remember, our communication protocol was 2 bytes for a write. First byte being the address to write to. Second byte being the value to write. Now then. First we want to setting device parameters. Now I need to do feature requests here now, don't I? And that's just what the API looks like. Do we have the actual API documentation at all? Evidently not. Useful. How to build it? I don't need to know how to build it. View code. Documentation. No, just a couple of pictures. Do we have a generated document to read? Oxygen, main page, API reference. Doing anything? Nope. For general information, see the source repository. Just round in circles. Okay. So to get the documentation, I'm going to have to check out the repository and build the documentation myself by the looks of things, unless I can find it somewhere else. Hid API documentation. Oh, go away, Google. Go away. Right, hid API documentation. There we go. Hid API's documentation. API. Send feature report. Right, send feature report. Now we've got to remember what all the different parameters are. I'm only actually using one parameter at the moment, which was the clock delay, I think, was it I was using? Yeah, FT clock del. Let's copy these actually, shall we? So the clock del. So if I set buff 0 to be ft clock del and buff 1 to be, let's go for 128. Now it would be send feature report. I mean, this is very much lacking, this documentation. That doesn't actually tell you how to use it. It just says there's a buffer. But there's also going to have to be a handle, I would imagine, isn't there? Doesn't say if there's anything for the length of the buffer. Right, that's useless, that. So let's have a look. Hid API, hid API H. Let's look in the header file, that's usually the best bet. So we want send feature report. Send a feature report to the device. Feature reports are sent over the control endpoint, blah, blah, blah. Calls to SID send feature report will always contain one more byte than the report contains. For example, if a HID report is 16 bytes long, 17 bytes must be passed. The report ID, or 0 for devices which do not use numbered reports, followed by the report data. This is why I started my report, my features on value 1, because 0 is always a special case for these. So we have the handle, we have the data, and we have the length. So we have the report number, we have the report value, send report, feature, handle, buff 2. So that should set the speed of communication on the bus. I will also do a just to be on the safe side, setting feature 1 to be 0. Feature 1, of course, was used by the bus type selector. 8088 is the only one that's coded, which is 0. So that should configure the bus to be the right format. And then I do a, is it hid write? Write an output report. Data and length again. So I do hid write handle buff 2 should do the job. Actually, I'm going to write a make file quickly. Bus emu dot o cc minus o bus emu dot o minus I user include hid API l hid API USB, was it? Oops, that's the point. That needs to go in C flags, doesn't it? Come on, what are you doing? Give me a thank you. C flags equals that. HID send feature report not declared. Did I? Oh, oops. I missed the HID off it, didn't I? It's HID send feature report. And the second one. Okay. Well, it thinks it worked, but I've no way of telling at the moment. So now it's time to bring out the big guns. Time for a little bit of logic analyzer goodness. Dream Source Lab logic analyzer. This is such a gorgeous bit of kit. And wires, there we go. Right. Let me connect up my logic analyzer. Get the colours right so that I know what I'm doing. Start off with the one with brown on it into channel 0 to 3. So we've got black, brown, red, we've got grey. Hang on, we've got strange colours here. Is this the right lead? We've got brown. These are in weird colour order. We've got grey, grey, brown, orange. Right, so grey, they've got, of course, because they're using black for ground, they don't want to be using black for 0, so they use grey for 0. 1, 2, 3 for orange, into the yellow one now. Yellow, green, blue, purple. So 4, 5, 6, 7. And then we repeat for the next set. That's right. Okay. That's 16 channels of logic analyzer goodness. I'm going to need some glasses for this. The curse of getting old. Can't see what I'm doing half the time. Okay. So I'm using A0 to A14 on this. So I shall start out with, let's connect a ground up. Connect these in sequence A0, A1, where's the red one? 2. It's good that they chose to use proper standard colour coding for these cables. When you know your resistor colour codes off by heart, these colour codes on the cables are identical. Apart from, of course, black for grey. It's just simple rainbow. There's the green on 5. Blue on 6. And purple on 7. Now, we have here a slight bit do we have a bit of confusion on here? We might have. Let me just bring up the pinout, because there's a slight twisting of the numbers because of this here being the ICSP programming header. So as far as port B is concerned, it actually goes, I think it's 0, 1, 2, 3, 4, 5, 6, 8, 7, 9, like that. But it might just be that it's straight through. So you got 30, 31, 32, 33, 34, 35, 36, 7. Yeah, it's all just numbered straight through. I thought it probably was, all been mapped nicely. It's a long time since I last looked at the chip kit boards, to be honest. I've been doing too much work with the RP2040 recently instead. And that's a lovely chip, but as with all things Raspberry, it's a nice idea and it's almost a good implementation, but there's always something lacking. And with the RP2040, it's a lack of a decent USB interface. So really good, powerful chip, dual core, high speed, high frequency. The PIO, programmable I/O system on it it's good, but it's not amazing. It is lacking in certain fundamental ways. You can't really do too much interaction between PIO and the internal CPU. It's all done through FIFOs and the odd interrupt, and there are bits about it which are awkward. Like there's no way of doing any sort of timeout on waiting for a signal and things like that. So it's good, but it's not perfect. But that's the USB on it. It's USB 1 only, which is somewhat limiting when you want to do this sort of thing. I mean, I would use the RP2040 for this job if the USB was good, but it's not, so I'm not. That's why I'm using the chip kit, because the USB is so much better. Right, I've got that connected up. Let's get the USB. Plug that in. Okay, now I shall need the software for it, DS View, and it finds it, the DS Logic U3 Pro 16. And how are we looking? 1 megahertz, that's way more than I need. Let's go. It should be going at about, well, actually, you know what, let's stick to 1 megahertz. And just do a quick test run. There we go. Now let's take this up. Let's do a minute's worth just for the moment. Although, no, don't want to. 10 seconds should do the job. Let's just queue this up. Start. Run that. Stop. Do I see anything? I see something happening here. And zoom in on here. I think this is just a brief blip. Oh, there is definitely something happening. There's 4 clock pulses by the looks of things, and that'll be the right pulse. So let's label this as clock. Label this as right. I think I had that as read, didn't I? Let's have a look at the firmware here. Yeah, so it should have D0, D1, D2, D3, D4, D5, D6 and D7. Then it should be A0, A1, and yeah, A2, of course. Then I've got write then read, write then read. Right, that looks like it was doing a read cycle then. Oh, yes. That's a good point. Because the address has gone 101. Or, sorry, yeah, which is, like I mentioned earlier, with the reports, the feature reports, port 0 is a special case. And doing a HID write is also a special case. So what I'm going to have to do is doing a HID write with the first byte of 0 is a special case and it loses that byte. So what I'm going to have to do is prefix every write with an extra byte. Let's just do that in here. If I, instead of using a 2-byte buffer, use a 3-byte buffer. And send a 0 followed by what I want it to have. That should now do a write rather than a read, but that read was encouraging. So if I run that again, and see if I can find it. Is there anything there? Oh, there's definitely something happened there. This is getting awkward. What I'm going to do actually is set a falling edge trigger on the clock. I've just realised. You haven't been able to see a thing that I've been doing here, have you? There we go, that's what you should be seeing. God, I'm an idiot. Right, yeah, so we're in DS view here. I've labelled all my traces. I've just set a falling edge trigger on the clock here now so that when I run this, it starts at that right point and I'm instantly zooming in on where it should be. Right, so we have interesting. That's not what I was expecting to see from the data. That's all going to 0 rather than going to alternating ups and downs. Although there's alternating ups and downs later on here. I think that is mainly it being slow to change the pins because of the Arduino API. Let's turn that off. So we've got first clock setting the address to 000, which is already set. Second clock, we've got setting the data to the alternating 101001 of OX55. Then we've got the write occurring with another clock. Have we got enough clocks here? We've got 1, 2. We seem to be lacking a clock. Let's just increase my resolution. Not 10 seconds, oh, 1 second. Actually, I can get away with just 100 milliseconds, I think. Except I'm not seeing enough data. Come on. Hello. It's crashed. Okay. Waiting for a trigger, and the trigger just not happening for it. If I reset the board. Disconnect, reconnect. Can I get anything to happen? Nope. Okay, I'm gonna have to terminate this if I can. It's completely locked up. Kill all DSView. There we go. Get on. Get onto this screen, please. Okay. Right, let's try this again. 1 second at 25 megahertz. But with a trigger would help. Let's set these back up again. D2, D3, D4, D5, D6, D7, A0, A1, A2, clock, write, read, with a falling edge trigger on the clock, start, go. Okay, gets to 72 and then stops. Not happy at 25. Let's try that again. And we got D07, A012, 11 is the clock. It's going to crash again. I'm not going to worry about entering everything. Let's go for 10 megahertz. Start, run. Nope, crashing again. Nothing in D message. It's the problem with doing things with USB and the Linux, they don't always work right. Okay, let's go for 10 megahertz and 500 milliseconds. Start, run. Oops, wrong button. Let's do that again, shall we? I won't kill it this time. 500 milliseconds, 10 megahertz, start, run. Although that was 1 millisecond and it worked. 1 second and it worked. Where's the data? Is there any data? Navigating this program is not always very easy. Zooming in and out is iffy at best. There we go. I'm seeing the clocks now. I've got 1, 2, 3, 4 clocks. That's looking a lot more like it. Right, let's do something a bit longer now, shall we? Let's have a sequence of writes 55 AA, that's the inverse. And let's have an all zeros and an all on. Let's run that and see what we get. It's crashed again. It just locks up. Okay. Let's kill that. Why does it keep doing that? It is mighty annoying. Doesn't seem to do it if it's not got a trigger though. And it's not even loading now, is it? Trying to load. There it is. Found it. Right, let's go in that case for 20 seconds. 10 megahertz start. Just let it. Ooh, a demo device. And now it's decided to load a second one. Right, is it work now? Trying. Very trying. Nope. I've got a light flashing on the logic analyzer. Let's reboot the logic analyzer. There we go, it's found it now. 20 seconds at 10 megahertz. And start. Gets to 81% and just locks up. Okay. Over this side, please. Let's go for let's go for 4 megahertz. See if I can get it going for a bit longer. And run that and see what happens. Here is the data. 4 transactions. Okay. That looks reasonable. Let's just try adding a decode stack on this of a parallel decode. So our clock line I shall have as 11, which is the, no, 11 is clock. I want the right, which is 12. And then the data lines, 3, 4, 5, 6 and 7. The clock edge to sample on will be the falling edge. Okay, and see what happens there. Oh look, it's decoded our 55 AA00FF. That is looking pretty good to me. I would say that is a success. We have what looks like a working, though the timing is a bit ropey, 8088 bus interface. That's pretty good. Okay. Next. This is a very basic program so far. So what I am thinking is I'm going to need getopt. I can never remember how to use getopt. But the man page has a very nice example. Normally, there it is. So, let's have a look. Let's have opt equals get opt. Argc argv. What do I want? I want B for bus type, I think. And let's have a simple write. Address, write and read. For the moment. And let's have a have the delay settings all capitals, I think. So have C for the moment for the clock delay. I think that should do for the moment. Okay, so I need what I'm going to do actually is put this after here. So that during the processing I can do if strcmp opt arg 8088 let's do a set feature 1 0. I'll need to pass the handle, of course. So now I do void set feature, and this is a hid device star handle INTF INTV and where are we? I'm just using a char, aren't I? Char buff 2 buff. I know I could do this with curly brackets, but I prefer to do it explicitly like this. Buff 1 equals V and hid set. Is it set or send? Send feature report. Okay. So in here then I can put all the different bus types when I create them. And C, I want set feature ft clock del a to I opt arg case A address equals, I will need to have something to put the address in. Address and data val. No, I'm going to use str2l for this. The address. Because str2l can deal with things like the OX prefix. So I shall have W for write, data val equals str2l handle null 0. What would I be doing handle for? Optarg. Idiot. And for a read, what I'm going to do, I'll try and be cunning here, it may backfire on me. Data val equals -1. Okay, so those should be done in the options. Although actually, thinking about it, I can be slightly more, even more cunning, I think. And do write val handle, comma, address, comma, str2l optarg null 0. Actually, I'm going to do that here as well. Keep it standard. Yeah, what I'm going to do is printf %d o2x to %o2x. Yeah, go data val equals str2l optarg null 0. here, data val equals read val, handle address, O2 that way, %O2, data val address. Now I just need to write these functions. So I need void write val device h, comma IDA INTV, char buff 3, buff 0 equals 0, buff 1 equals address, so A, buff 2 equals V. Hit right, handle buff 3, okay. Read val. Now this is a little more tricky. Buff 0 is still OXO. Buff 1 is the address. Hid right, handle buff 2. Now hid read. So I do a hid read timeout, didn't I say? Hid read timeout. The milliseconds, that's useful. Hid read timeout, handle, buff, should be only 1. With a 1 second timeout. That should then give me read functionality, I hope. This won't compile. Nope. Handle undeclared. Okay. That's better. Okay, let's see what happens then if I do a bus of 8088, an address of 3, that should be all of the addresses high, with clock delay of 255, and write a value 55. Let's give me a true on the clock. Start. There we go. We have our 55. Now what would happen? Hang on. Let's get stuck in a loop. Why has that got stuck in a loop? Where's my get opt? Not sure why that was stuck in a loop. It had done that. While opt equals get opt argc argv, the options you want, not equal to 1. Oh, minus 1. That's why. pesky minus makes all the difference. Okay, let's bring this back. And we start that packet there. The content of received packets are not as expected. It doesn't like that, but it seems to be still running. So now I run that again, and this doesn't work because this has crashed again. What happens if I make the device disappear? This really doesn't like losing the device. Kill it. Okay, trigger on 11. 4 megahertz was good. Let's give it a whole minute. Start. Go. Stop. Let's add my parallel decoder. Clock is 12. All 8 data bits. And a falling edge. There's the 55. Now, theoretically, I should be able to do something like this. And if I start that and go bang, and then stop, zoom in, there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, A. That is looking very good. Now I've got no way really of testing the reading on this now though. You know what I need for testing the reading? I need a bus emulator system that can generate signals. Basically I need 2 of these, don't I? So I could do with a second one of these connected to this one outputting the other one reading, but outputting really is the main functionality that I'm after at the moment. So I think this is pretty much ready to be used for some testing. There's not really that much more I can do with it now. I could add checking for the serial number so that I can have 2 of them on at once and differentiate between them. That could be useful. Not necessary though, but what I am going to do though, I think, is I'm going to set up a GitHub repository for this. Let's go on to GitHub. I do this on my streaming computer, so you can't see all my private stuff. I don't care about my stuff. There's customer repositories on there that, because I'm logged in as me, which are normally private, which can't really let you see. Non-disclosure agreements and all that. As you can imagine, my streaming computer is a little bit slow at the moment because I'm doing this stupid thing called streaming. A lot of disk activity with storing all the video data. So Firefox is taking forever to load. Is it even going to load? No, it's not. Come on. I need some more SSDs in here, I think. There it goes. Okay, on to GitHub. Sign in. Eventually. And go to my projects organization. Create a new repository. This is busemu. Okay, create a repository and copy that link. Right, let's have a look. Get in it. So we want the make file and the C file. And for the firmware, we want the make file and the INO file. That should be it. Let's make a README as well. Simple bus emulation system for the chip kit MZ Lite for emulating microprocessor and similar device buses. That'll do for now. Nothing else I need there, is there? No. Okay, git commit initial import git remote add origin git push -u origin master. Okay. Browser GitHub Magenco projects plus emu. Except I cannot type. There it is. If anybody wants to help out implementing more buses on it, that would be brilliant. But there's a basic framework for the code working. So now it's just a case of adding all the extra functionality, all the different bus types, a few extra bells and whistles, maybe a sort of scripting language sort of thing. Yeah. But I think I've done enough today. Yeah, right, well, we have a working system. That was not bad, really. My strange brain can be useful sometimes because I never really design software. I see the software in my head and then write it out into the program, and it just works. I just sort of see I just see the shape of the software, and it's just there. So it's wonderful being able to program like that, but not everyone can, obviously. It's a strange talent of mine with my My weird brain. So anyway, there it is. It's working. It's usable. The DSView software is touchy, it has to be said. The hardware is really, really good. As with so many of these makers of these sort of hardware things, the hardware is absolutely top notch. It is brilliant. But the software that accompanies it leaves a lot to be desired. I mean, this is good, this one, because it's based on SIGROC, which is open source. So the whole of their software suite is open source. They've taken SIGROC, added their own stuff to it, and re-released it as DSView. They've got their own custom interface to it, rather than the PulseView interface, but it's very similar in a lot of ways. But as with so many of them, it doesn't always work quite right. Part of the problem, I think, is that so many of them develop first and foremost in Windows and then port it to Linux. And most of their developers are Windows developers, and they don't really have a deep understanding of the Linux USB system and things like that. And it tends to be slightly lower quality Linux, unfortunately. It would be nice if it was supported directly in the master branch of SIGROC rather than using their own branch of it, in which case it would probably get better community support rather than just their own in-house developers. I think it's all on GitHub, so you can do your own development for it if you really want to, but how open they are to other people making pull requests, I'm not sure. So it would be better if they had, instead of sort of created their own completely separate fork, taken SIGROC, added to it, and then fed that back into SIGROC, so that SIGROC itself was their suite, but alas not. But it works most of the time. It's when you start to try and do more complex things on it, like protocol decoding or triggering and things like that, it seems to lock up slightly. But it's a nice bit of kit, though, for all that. So, yeah, and it certainly helps when developing this kind of thing. So, yeah, I'm going to shut up now. You've heard enough from me. I've done what I can really on this today, I think. It's time for me to go and have a cup of tea. And no stream tomorrow, obviously it's a Friday. I do video editing on a Friday. Over the weekend, I'm going to try and get a bit of streaming done over the weekend, but I don't normally do that much. But I will hopefully have a look at this that I had delivered today. Let's go back to my desk view. This is courtesy of a good friend of mine. Drop that. This is the Zeltec Super Pro programmer. This is I suppose it's the predecessor to the EEPROM programmer that everybody uses these days, which is the Mini Pro. And this is the Super Pro. This is its big brother from early to mid 90s. This was, I think, 1993ish, 1994, around the time of my 486 actually. So it should go nicely on that. It's got its own 25-pin connector, which goes to a custom card on the ISA bus, which unfortunately, of course, is not available. But somebody very conveniently has reverse engineered it and has created an open source project for it, so you can make your own. And I have a couple of blank boards which I will need to populate. So I need to go routing through all my supply of old logic chips and things and see if I've got all the right ones. See what passive components I need to order, resistors, capacitors, whatever, that I don't happen to have in stock. It's 100% through-hole. I don't have a huge amount of through-hole passive components because most of my work is done with surface mounts. So I've got all the value resistors and things that I would need, but they're just not as through-hole. So I'm probably going to order a batch of through-hole resistors of the right value. So yeah, I shall be building that up at some point. I may just, over the weekend, pull this apart and have a look inside. I have seen pictures of the inside, and it is packed full of good old school chips. So it'd be nice to actually see what the chips are in there and quite how it works before I then move on with building the board and then trying it out in my 486. I'll also try it out in my 5110, see if it'll operate in that. Unlikely because it's a bit new for that, so the software might not work on it. And the hardware certainly, well, it's an 8-bit ISA card, so that would have no problems working, but it's just whether the software that goes with it will work on an 8088 or whether it needs a slightly more powerful processor. So that's what I'll have a look at over the weekend, possibly. Or maybe next week. We'll see what happens this weekend. But that's it for today then. Thank you for joining me. If you want to find me, I'm on Discord. If you're watching on YouTube, you should join me on Twitch sometime live. It's much more fun. And yeah, I shall see you soon.